Welcome to this video on the dynamic Prime Cantor Set, a fractal structure intricately woven from the properties of prime numbers. Prime numbers act as both the blade and the timing for carving this set. The blade, $p_k plus $1, determines the subdivision, and the timing, $p_k, defines which subintervals are removed. The construction begins with the unit interval, 0, 1. At each step, $k, the process splits the intervals and removes parts based on the primes, leading to a dynamic structure. Steps 1 through 3 demonstrate the non-uniform nature of the set. The rule changes at each step, causing the gaps to vary and giving the fractal its alive characteristic. The prime number theorem ensures that the total measure of the set tends to 0, confirming its Lebesgue null status. However, the decay is slow enough for the Hausdorff dimension to approach 1. The set shares the classic topological properties of a Cantor set. It is compact, perfect, and totally disconnected, reinforcing its fractal nature based on prime logic. As the construction steps progress to the limit, the Lebesgue measure becomes 0, while the Hausdorff dimension approaches 1, indicating a highly dense yet hollow set. The Hausdorff dimension converges to 1 due to the vanishing removal rate, a consequence of the prime number theorem. This set is, quote, space-filling dimensionally but remains hollow in measure. The convergence to dimension 1 is ultra-slow, quantified by logarithmic decay terms based on the construction step, $k, or the geometric resolution, $epsilon. Prime randomness literally sculpts local porosity. Wide prime gaps create large, smooth regions, while narrow prime gaps result in a chaotic, crowded texture with intricate fine details. The dynamic Prime Cantor set exhibits multifractality. Preliminary analysis hints at a continuum of local dimensions, suggesting a single Hausdorff dimension is insufficient to fully describe its structure. The set can be embedded as a hyperbolic geodesic tree in the Poincaré disk, highlighting a deep, prime-driven branching architecture on the boundary circle, $s$1. Embedding in hyperbolic geometry, specifically the Poincaré disk and its dual tree, bridges Kleinian group geometry with analytic number theory, encoding primes within its limit set. The dynamic Prime Cantor Set is a fusion of mathematical worlds, linking fractals, measure theory, prime distribution, and hyperbolic geometry. It serves as both an intuitive teaching tool and a research model. Future research avenues include rigorous proofs, spectral analysis using the hyperbolic Laplacian, and quantitative analysis of local porosity, alongside exploring alternative construction rules. In conclusion, the dynamic Prime Cantor Set is a significant outcome of the conversation between number theory and fractal geometry. Key academic foundations include work by Falconer on fractal geometry, Bearden on discrete groups, and the prime asymptotics provided by Hardy, Wright, and Apostel.